Hello everyone, welcome to Play Learn Planet. Today we will explore the fascinating world of sensors that power modern vehicles. These intelligent components work together with various control units to make our cars safer, smarter, and more efficient. Throughout this presentation, we'll dive deep into different types of automotive sensors, how they function, and why they are essential for today's advanced driver assistance systems and autonomous driving technologies. Let's begin our journey into the world of automotive sensors. Modern vehicles are packed with advanced electronics. At the heart of this system are sensors, devices that detect changes in the environment and convert them into electrical signals. These sensors continuously monitor everything from vehicle speed and engine temperature to surrounding obstacles and driver behavior. Together with electronic control units, ECUs, they enable features like automatic braking, lane keeping, adaptive cruise control, and much more. An ECU, or electronic control unit, is an embedded electronic device, a digital computer that reads signals from sensors to control important car functions like the engine and other automated operations. ECUs are typically mounted in the engine compartment or the passenger room, depending on their function. Key types of ECUs include the engine control module, electronic brake control module, powertrain control module, and vehicle control module. The ECU utilizes closed-loop control to monitor outputs and control inputs, managing engine emissions and fuel economy. It gathers data from dozens of sensors, performing millions of calculations each second to optimize performance. While modern ECUs may have smaller, less powerful processors than PCs, they run highly efficient code. An average ECU's code uses less than 1 megabyte of memory. ECU applications allow for adaptable engine control. For slower tracks, the system can make the pedal movement very sensitive. For high-speed circuits, it adjusts for a small throttle input to result in full engine acceleration. Engine sensors are a critical part of the system, including the oxygen sensor, throttle position sensor, crankshaft position sensor, map sensor, engine coolant temperature sensor, and mass airflow sensor. The oxygen sensor is located in the exhaust system and measures the ratio of the air-fuel mixture to help control emissions and performance. The throttle position sensor monitors the position of the throttle in an internal combustion engine, usually located on the butterfly spindle. The crank position sensor monitors the crankshaft's position or rotational speed. This information is used by engine management systems to control ignition timing and other parameters. The MAP sensor, or manifold absolute pressure sensor, is shown here in schematic view, detailing its components. The MAP sensor provides instantaneous manifold pressure to the ECU. This data calculates air density and the engine's air mass flow rate, which determines the required fuel for optimum combustion. Some engines use a MAF sensor instead of a MAP sensor. The coolant temperature sensor measures the temperature of the engine coolant. These readings are sent to the ECU to adjust fuel injection and ignition timing, and can also control the electronic cooling fan. It works based on resistance changes with temperature. The mass airflow, or MAF sensor, is another critical component, shown here in a side and front view, detailing its internal elements and connectors. The MAF sensor is used to find the mass flow rate of air entering a fuel-injected internal combustion engine. This information is vital for the ECU to balance and deliver the correct fuel mass. Since air density changes with temperature and pressure, mass flow sensors are often preferred over volumetric flow sensors for calculating the quantity of intake air in each piston stroke. Speed sensors are machines used to detect the speed of an object, usually a transport vehicle. They include wheel speed sensors, speedometers, pedometer logs, pitot tubes, airspeed indicators, piezo sensors, e.g. in a road surface, LiDAR, ANPR, where vehicles are timed over a fixed distance. Moving beyond engine sensors, speed sensors are essential machines for detecting the speed of an object, commonly a transport vehicle. They include a variety of devices. One example is the wheel speed sensor, also known as a vehicle speed sensor or VSS. It is a type of tachometer used to read the speed of a vehicle's wheel rotation, often consisting of a toothed ring and pickup. The speedometer is a device that measures the instantaneous speed of a land vehicle. Types include the eddy current, electronic, and bicycle speedometer. The image displays a schematic of a mechanical speedometer. The various types of speedometers include eddy current speedometer, electronic speedometer, bicycle speedometer. A piezoelectric disc generates a voltage when deformed. Change in shape is greatly exaggerated. A piezoelectric sensor is a device that uses the piezoelectric effect to measure pressure, acceleration, strain, or force by converting them to an electrical signal. In the automotive industry, piezoelectric elements are used to monitor combustion when developing internal combustion engines. Types of vehicle sensors: rain sensor, parking sensor, air conditioning sensor, oil sensor, fuel gauge, radar gun, water sensor. Rain sensors: photodiode, LED. Automotive rain sensors detect rain falling on the windshield of a vehicle. One of the more common rain sensor implementations employs an infrared light that is beamed at a 45-degree angle onto the windshield from inside the car. If the glass is wet, less light makes it back to the sensor, and the wipers turn on. Rain sensors: photodiode, LED. Automotive rain sensors detect rain falling on the windshield of a vehicle. One of the more common rain sensor implementations employs an infrared light that is beamed at a 45-degree angle onto the windshield from inside the car. If the glass is wet, less light makes it back to the sensor, and the wipers turn on. Oil sensors are used in automotive or oil sensors and oil analyzers, industrial machinery applications to sense oil levels and check for contamination, particulates, viscosity, temperature. Oil sensors and oil analyzers are also known as ferrography instruments. A fuel gauge is an instrument used to indicate the level of fuel contained in a tank. As used in cars, the gauge consists of two parts: the sensing unit, the indicator. Actuators. What is an actuator? Actuators are devices used to produce action or motion. Input: mainly electrical signal, air, fluids. Greater than electrical signal can be low power or high power. Actuators output can be position or rate, i.e. linear displacement or velocity. Classification of actuators: pneumatic, hydraulic, electrical/electronic. Pneumatic actuators are specialized devices that convert the potential and kinetic energy of compressed gas, usually air, into mechanical motion, providing power to automated systems, machines, and processes. Types of pneumatic actuator. Pneumatic actuators are made in a wide variety of sizes, styles, and types, including the following: single-acting with and without spring return. 2. Double-acting. Single-acting spring return cylinders use pressurized fluid or air to produce work in one direction, usually extension, while an internal spring forces the piston back to its original position upon pressure release. They feature a single port, offering a cost-effective, simple design for applications like clamping or lifting. Double-acting cylinders use pressurized fluid, air or oil, on both sides of the piston to power both extension and retraction, enabling high-force, high-speed movement. They offer precise motion control, especially with integrated cushioning, to manage high-speed impacts, making them ideal for applications requiring consistent, two-way power. The image illustrates the schematic diagram of a hydraulic intensifier system commonly used for high-pressure water jet cutting or cleaning. It displays the flow of hydraulic fluid and water through various components to generate ultra-high pressure output. Intensifier and attenuator. The central component increases water pressure, while the attenuator stabilizes this pressure for consistent cutting. Hydraulic system. An electric motor drives a pump, with directional control valves managing the flow of hydraulic fluid to operate the intensifier. Water processing. Inlet water passes through filtration before being pressurized and sent to the cutting or cleaning component. Control system. Electronic controls, such as a PLC, programmable logic controller, manage the overall operation. A hydraulic drive system is a drive or transmission system that uses pressurized hydraulic fluid to drive hydraulic machinery. The term hydraulic actuator refers to a device controlled by a hydraulic pump. A familiar example of a manually operated hydraulic actuator is a hydraulic car jack. Typically, though, principle used in hydraulic actuator system. Hydraulic actuator. The diagram illustrates the primary components of a double-acting hydraulic cylinder, which converts fluid pressure into linear motion. Key components: piston and rod assembly, the central moving part. The piston divides the inner space, while the rod extends outside to move a load. Barrel. The main cylindrical body that holds the high-pressure hydraulic fluid. Sealed chambers, the two internal areas separated by the piston. Fluid entering one side pushes the piston, while fluid on the other side is exhausted. Ports, the entry and exit points for hydraulic fluid. Head and cap, the end enclosures. The head includes a seal for the rod, while the cap seals the back end. Attached to machine member. The mounting point, island, used to connect the actuator to the equipment it operates. Working of hydraulic actuators. Hydraulic actuators, or hydraulic cylinders, typically involve a hollow cylinder having a piston inserted in it. An unbalanced pressure applied to the piston provides force that can move an external object. Since liquids are nearly incompressible, a hydraulic cylinder can provide controlled, precise linear displacement of the piston. The displacement is only along the axis of the piston. The piston forms sealed, variable volume chambers in the cylinder. System fluid forced into the chambers drives the piston and rod assembly. Linear movement is produced. Hydraulic actuators or hydraulic cylinders typically involve a hollow cylinder having a piston inserted in it. An unbalanced pressure applied to the piston provides force that can move an external object. Since liquids are nearly incompressible, a hydraulic cylinder can provide controlled, precise linear displacement of the piston. The displacement is only along the axis of the piston. The piston forms sealed, variable volume chambers in the cylinder. System fluid forced into the chambers drives the piston and rod assembly. Linear movement is produced. Classifications of hydraulic actuator. Cylinders are typically classified by operating principle or by construction type. Single-acting or double-acting. Tie rod, mill, threaded end, or one-piece. Single-acting cylinders exert force either on extension or retraction. They require an outside force to complete the second motion. Double-acting cylinders generate force during both extension and retraction. Directional control valve alternately directs fluid to opposite sides of the piston. Force output varies between extension and retraction. Single and double-acting cylinders are the primary actuators used to convert fluid power into linear motion. The fundamental difference lies in how they handle the retraction stroke. Single-acting cylinders rely on external forces, like gravity or springs, while double-acting cylinders use pressurized fluid for both directions. Electrical actuators in control systems. These systems are crucial because they offer high precision, ease of control, and clean operation. Thank you for watching. Please like, share, and subscribe to Play Learn Planet for more videos like this.